Alright, welcome back. This is still Fluid Mechanics homework number 1, but we are now on part B. Part B is broken up into 3 different problem statements. The first of which is by integrating the pressure forces on a cylindrical container, derive an expression relating the minimum wall thickness necessary to the pressure, height, radius, and tensile strength of the wall material. So the first thing I'm going to do here is I'm actually going to draw a diagram of our cylindrical container that we are looking at. So here's our cylindrical container. And we can imagine that this cylinder is filled with a fluid of sorts. And this fluid is creating pressure forces onto the face of the cylinder's walls. So I'm going to draw a top-down view as well so we can get a better idea of what these forces are actually um, doing to our cylinder's walls. So we can imagine this is filled with fluid. And I'm going to take a cut through half of our cylinder here. And the fluid will be acting and creating pressure force onto the walls of our cylindrical container here. And as we can see, the I'm going to label this the vertical direction. I'm going to label as our y direction, and our horizontal direction will be our x direction. So as we can see, the forces acting in the y direction have a equal and opposite force acting on the other half of our cylindrical container. So the forces in the y end up canceling each other out. However, the forces acting in the x direction will end up adding up and trying to pull our cylindrical container apart. And we are going to look at the cross-sectional area as our limiting factor for our cylindrical container. So the cylinder is now being held by the material of our wall. So we're going to label this as big T for wall thickness. And we're really interested in the tensile strength of our material because that's really what's holding our cylindrical container together from these forces acting in the x direction. So we have tensile strength, and we're going to label this as sigma. And we know tensile strength is a force distributed over an area. So what area are we looking for? So I'm going to come over to our diagram over here, and we are looking for um, the area that is being stressed by these forces. So I'm going to label this as our height, and we know this is our wall thickness. So the rectangular area here and also on the other side is being stressed by these forces in the x direction. So that's the area we're looking at. So we have A equals 2 times our height times our wall thickness, height of the cylindrical container. So now we have our sigma equals our force over 2ht, or force equals sigma 2ht. So how do we calculate and add up the forces acting in the x direction? Okay, so our next step is to look back at our cylindrical container diagram and find a way to add up the pressure forces acting in the x direction. And for this, we will use integration. So coming down here, we are looking at the integral of the forces in the x direction. And we're trying to add them all up. And we know these are a pressure times some area. And the way we're going to find this area is, remember, if we have a circle with our radius here, this will be big R, and we have some differential angle d theta, this length right here will be r d theta. And we also need to remember to multiply this length by our height to get this differential area. So our area, or our differential area in this case, would be r d theta times h. So we end up getting the integral of pressure times radius times height d theta. And we also need to parameterize our integral by making the pressures into the x direction. So here we have PdA, and we remember that we're looking for these forces in the x direction, so we need to multiply this by cosine of theta to get these forces in the x direction, if this was theta. So we're also going to multiply this by theta, or cosine theta, rather. Now we need to set our limits of integration. So we're acting from the bottom to the top of this, I guess you could call it a circle looking down at our cylinder. And we know this is negative pi over 2, and this is pi over 2. So those will be our limits of integration. So we have the integral of PRH d theta cosine theta. We know that P, R, and H are constants, so we can pull those out. And we are left with the integral from negative pi over 2 to pi over 2 of cosine theta d theta. And we will integrate this. So we have PRH sine theta of pi over 2, negative pi over 2. So this leads into PRH times 1 minus negative 1. So we end up getting 2 PRH as our force acting in the x direction. So we can compare this to our force here. So this one was F equals sigma 2ht, so we're just going to call it 2 sigma ht. And we know that equals 2 PRH. So if we divide our 2 over, our h over, they cancel. And we can get our thickness, our minimum wall thickness, to be PR over sigma. This is our expression. So let's get into part 2 of part B. The problem statement states, repeat B1 for a spherical tank, again relating the minimum wall thickness to the pressure, radius, and tensile strength. And remember that B1 says, by integrating the pressure forces on a cylindrical container, derive an expression relating the minimum wall thickness necessary to the pressure, height, radius, and tensile strength of the wall material. So now we're looking at a spherical tank. So first thing I'm going to do, once again, is draw a diagram. So we have our diagram. So we're going to draw the two hemispheres of our spherical tank. So we'll start in the middle here. One hemisphere and the other one. And I'm also going to draw our thickness of our wall. And as you can imagine, our spherical tank is filled with fluid and there's pressure forces being applied to the walls of our container. So The forces in this case, as compared to the cylindrical container, are working in 3 dimensions. So they're working in a z component, a y component, and also an x component. But the process is similar, where we are trying to identify one of the forces. So we're going to identify the x force in this case, because these forces, when added together, will pull our two hemispheres apart at this boundary right here. So the first thing we got to do is figure out what this area is right here. So this area is equal to 2 pi r being our radius, times our wall thickness, t. And the force needed to pull our two hemispheres apart is this times our tensile strength, sigma. Alright, so the next thing I'm going to do is I'm going to look at a projection, a vector, that is attached to one of the walls of our spherical tank. So this is our z, this is our y, this is our x. So we can imagine some vector that comes out and is touching the inner wall of our tank. So this length would be r. And it would be related to the xy plane by some angle theta. And if we look at a projection of this vector down, it would be related to the x-axis by some angle phi. So what we want to do is we want to basically chop up our sphere into differential areas, and then once we have these areas, find the pressure force, because remember the pressure force is pressure multiplied by some area, all in the x direction. So we're going to draw out this differential area. So it's got, kind of looks something like this. Oops, let me redraw that. Something like that. So we need to find the lengths of these two arcs right here in order to find this differential area. So we're trying to find dA. So we know that this angle is theta. So the angle between this length right here would be d theta. And the length would be d theta times r. So this is that length covered. Our next length, if we project this down onto our xy plane, we can look at this length, which would be r times cosine of theta, and this would be multiplied by some angle right here, d phi. So this length, this one's this one, and this length would be equal to r cosine theta d phi. So our dA, our differential area, would equal r squared cosine theta d theta d phi. Okay, the next step is remember our differential force here is equal to pressure times some area. So our dFx which is what we're interested in, all the forces in the x direction, would be equal to P dA times the cosine of theta times the cosine of phi. So let's write this all out now that we know what dA is. So d of x is equal to pressure times our dA, which was r squared cosine theta times another cosine theta, which would make this cosine squared theta, cosine phi, d theta, d phi. So our next step is to integrate our dfx. So we get, these two are constants, so we get p and r squared on the outside times the integral from pi over 2, or sorry, from negative pi over 2 to pi over 2, because once again we're looking for from here at the bottom of our sphere to the top, of cosine squared theta d theta times another integral of cosine phi d phi from negative pi over 2 to pi over 2. Look at each of these integrals separately. So we're going to start with the easier one, which would be cosine phi d phi. So let's start here. We have the integral of negative pi over 2 to pi over 2 of cosine phi d phi, which turns into sine of phi from negative pi over 2 to pi over 2, which is equal to 1 minus negative 1, which is equal to 2. So this ends up going to 2. Okay, so the next integral we have to do is our cosine squared theta d theta. So let's write it out. From negative pi over 2 to pi over 2 of cosine theta times cosine theta d theta. So the way we're going to do this is we're going to use integration by parts. So we need to choose our u, v, dv, and du. So for u, I'm going to choose cosine theta. For dv, I'm going to choose cosine theta d theta. So du equals negative sine theta. And v equals sine theta. So now we use our integration by parts, and we get cosine theta, sine theta, from negative pi over 2 to pi over 2, plus the integral of pi over 2 to negative pi over 2 of sine squared d theta. And we know that sine squared d theta is equal to 1 minus cosine squared theta. So I'm going to rewrite it as that in this case. And on the other side here, we have the integral from pi over 2, or negative pi over 2 to pi over 2 of cosine squared theta. So the next step will be to look at both of the parts of our integration by parts. So if we do this integral cosine theta sine theta from negative pi over 2 to pi over 2, it ends up going to 0. So we can cross this term off. And if we notice, we have cosine squared theta over here, d theta, and we also have cosine squared d theta on the other side. So we're going to add this cosine squared theta d theta, or add the cosine squared theta to the other side. So we end up getting a 2 on the outside, the integral of negative pi over 2 to pi over 2 of cosine squared theta d theta equal, this is already gone, to the integral of pi over 2, negative pi over 2 of just 1 d theta. So then we get theta from negative pi over 2 to pi over 2. And we get pi over 2 minus negative pi over 2, which gives us pi over 2. So this equation gave us pi over 2, this integral. This integral gave us 2, and then we have pi r squared. So we have d of x is equal to 2p p r squared times pi over 2. And these 2's end up canceling out. So we have p r squared times pi. And now we can compare that to our original f, which was 2 pi rt sigma. So 2 pi sigma t 2 pi rt sigma equals p r squared pi. And now we solve for t. So t equals, the pi's cancel out, one of the r's cancels out, so we get p r divided by 2 sigma. And this is our expression for a spherical tank. Okay, so now on to problem statement 3 of part B. It states, explain how the results in parts B1 and B2 could be obtained through a judicious choice of a dividing plane through the cylindrical and spherical tanks. So the first thing that I'm going to do is write down our results from parts B1 and B2. So B1 was our cylindrical tank. And let's scroll up to see those results of what we got. It was equal to 2 sigma ht equal to 2 prh. So B1 is equal to 2 sigma ht equal to 2 prh. So our t in this case was equal to pr over sigma. And let's look at the results of our spherical tank, B2, which were 2 pi rt sigma equal to pr squared pi. So now how could these results be obtained through judicious choice of a dividing plane through the tanks? So first I'm going to start with the spherical tank. So we're going to draw it out. And what we did in B1, remember, was we looked at the side surface of our cylinder, and we used an integral to add up all the forces acting in the x component that were pulling our cylinder apart. However, if we think about this in a different way, if we use a plane to cut our cylinder in half, and we think about the fluid on the opposite side of our container, it is applying a pressure force on perpendicular to this plane to keep our cylindrical container to not accelerate. So, what area would this plane be? It would be 2r times our height. And we remember that pressure force is a pressure times some area. So, the pressure force in this case would be equal to 2 PRH, which is exactly what we calculated with our integral in B1 by using a judicious choice of a dividing plane. Now the same can be used for B2 for our spherical tank. So let's draw that out. We have our two hemispheres, and we're going to cut the two hemispheres with a plane right through the middle, creating this spherical area. And we have our pressure force acting perpendicular to this area. This area would be pi r squared. So we would get force equals p r squared pi, which is exactly what we got from our integral in B2. So this is how a judicious choice of a dividing plane through the tanks can help explain the results that we got from B1 and part 2 in B2.